Okay, welcome back to another round of trying to build a 80s style vintage computer. So now that the CPU board is done, the next two boards, so I've got two separate boards here, are going to be firstly the RAM and then secondly the serial I/O. Now I do actually have a RAM chip, it has arrived. It's in this little box here. I've got it all set up. It's 1 megabyte of static RAM. But before I do that, I need to work out how we're going to get data flow working. So the Zilog Z80 has got two rather important pins. The first one controls I/O, and the second one controls whether or not we're getting memory requests. There's also a data bus request, but that's entirely different. That's to allow the data bus to send information between devices without the CPU interfering. So we're not going to worry about that one. So yes, we've got a memory request and an I/O request. Now, in order for those to function, I need some logic gates. So what's going to happen, there's going to be basically three different I/Os here. There's going to be the default, which will be a whole heap of these little delightful toggle switches. And that's going to be for entering information when the computer first boots up. Then we're going to have the RAM chip. And then finally, we're going to have some serial. So I've got some serial plugs in here, but I don't know quite what IC I'm going to need to control DB9 serial yet. That's something I'm still trying to work out. Anyway, so how I'm going to get it to work basically is I need a NOT gate, or two NOT gates, an AND gate to make a NAND gate. Now I want to make these out of discrete components, which we'll see in a few seconds. And how it's going to work is by default, if neither the if neither the memory request or I/O request pins are active, then the toggle switches will become active. So when you turn it on, neither of them are active, so therefore the toggle switches will be default. However, if I use the toggle switches to toggle it and say, I don't know, check I/O, then the I/O request pin is going to become active on the Z80, and so the toggle switches will become inactive. Same would apply to checking the RAM. I've gone with static RAM. I believe that means when there's no power, it keeps data stored on the chip. Might be wrong. They're pretty sure that's how it works though. So the idea is that, once you've entered some information on, you can load that back without having to re-enter data every single time you boot it up. But anyway, how I'm going to get that working is I'm going to have something along the lines of 24 transistors attached to the different pins. So for example, if the bus request pin is active, then all 8 of the data 0 to 7 pins, sorry, I'm going to rephrase that. If the memory request is active, then that'll send a signal to the base of 8 different transistors attached to the data bus, and that's going to basically say, oh, okay, this is active, therefore we can send information to the RAM and or get it back. So I ran out of memory on my camera temporarily there. So anyway, how it's going to work is that either the transistors will be activated through requiring a bus request, a memory request or an I/O request. Or if neither of those are true, then that makes the NAND gate active. So here are my gates I'm working on. At the moment, we've got an AND gate over here, and we've got two NOT gates. If I pull either this wire here or this wire here, I'll do this. Well, looking at the camera can be a bit tricky. You'll see that the LED is activated, so that's a NOT gate. As long as there's no power going in, there is power going out. With the AND gate, if I take either the red wire, or the white wire, then there was no power going out. But if both of them are in, then there was also power going out. So AND gate, NOT gate. And now it is time to combine them together like that cheesy 80s cartoon. And there we go. So this is now a NAND gate. If both these are unplugged, so there's no power going into A or B, there is power, and it's very faint, but there's power coming out of the output. However, if I plug both back in, boom, already it's gone off, and boom, gone off. Unplug this one first, nothing. If I unplug this one as well, there we go, there's the power. So that is a NAND gate, and that is what I'm going to be using for flow control for the data logic. Now, how does this work? Well, okay, so how does a NOT gate or NAND gate or an AND gate work? Well, it's relatively simple. We've got 3 pins on our transistor. We've got our base in the middle, which is the switch part of it. If there's power flowing in through the base, it allows power to go from the collector through to the emitter. We've got our emitter, which goes straight to ground here, and then we've got our collector. Now, collector is where the party happens in a NOT gate. We've got a 470 ohm resistor here. This is a 1K. It's technically connecting to the base. That's because the base is very temperamental. I think it's something like 0.7 volts maximum. So we don't want to fry our transistor, so we have a 1K resistor there. Anyway, 470 ohm resistor. So power goes along this 470 ohm, it gets to here. Now, if there's no power going through into the base, that means that this is not allowing power to pass through it. So the only option for the current is to go through the LED, or in this case through the blue wire to the NAND gate, and out of the circuit. However, if there is power going in through the base, suddenly it's got this much tastier avenue, path of least resistance, basic electronics principle, and it goes, oh, I'm not going to go to the LED and all that shenanigan, I'm just going to go straight to ground, okay? And so obviously, if there is power going in through the base, we do not have power going out through the LED. If there's no power going through the base, we must have power going out through the LED because that's how the circuit is completed. Okay, so what about our AND gate? Well, our AND gate's a little bit more complicated, a little bit different from our NOT gate. It's got 2 transistors. We've got one transistor here, and we've got one transistor here. Now, the first transistor, its collector is plugged straight into positive, and it goes in through here, and then the emitter plugs straight into the collector of the next transistor. So what happens basically is if we've got power going through these 2 wires right here, and then through the 470 ohm resistors into each of the transistors, we've got power can go through here, and then can flow through here, and it can flow out through the LED. This extra one here, that's just grounding for the voltage, okay? So voltage has to have grounding because logic flow is not a proper way to ground a circuit, and so if we didn't have this, nothing would happen, okay? We've got to be able to ground the circuit for the purposes of keeping the circuit complete. So anyway, power goes in through here. Let's say this one here isn't currently plugged in. Well, then the power can't go any further, and so the circuit isn't actually properly complete. If this one's plugged in, but this one's not, same issue. We've got power gets this far, but it can't go through this, and so the circuit is still not complete. Only when the bases of both these two transistors are actually receiving power does the circuit actually complete, and therefore we can get the LED to light up. So in some ways more simple than this, in some ways not. Finally, the NAND gate, well, it just combines the properties of both. Okay, so these work same as a NOT gate. Okay, so as long as there is not power flowing through both these 2 here, then power does flow out through the blue wires. And for the blue wires, that just plugs straight into the base here and completes this circuit and therefore lights up the LED. So quite simple. It's just a combination of both a NOT and an AND. That's what's called a NAND. Very inventive. So now that I've finished this, the next step is to work out exactly how I'm going to get this to function in terms of transistors for the data flow. Now, I don't know how that's going to work exactly, because as making this video, I just suddenly realized that, oh, wait a second, yeah, that's going to allow power to flow, from the CPU through to the RAM or whatever, but it's not necessarily going to allow it to flow backwards. So I'm going to have to do a little bit of thinking, but basically what I need to do is get it to switch based on different transistors activating based on this gate here. So I know the gate works now, great, that's the first issue solved. Next issue is working out exactly how the logic flow is going to function in the circuit. I'll catch you guys next time.